So moving on, we've got optimizing kinematic structures and IK parameters by combining reach and Optuna. Marc Bestmann. He's the robot assisted inspection and repair team over at the German Aerospace Center. He is their lead. I appreciate you taking the time, Mark, and it was great to see you and Michael like swap notes back and forth. So with that being said, Mark, the floor is yours. You should be able to share. So thanks for coming today.
Share. So I hope you see the screen now. Perfect. So yeah, you already mentioned the title. It's quite a long one. But I hope it will still be interesting. And yeah, if you're not too tired, at least in Europe, it's already quite late for workday. But you will then learn in my presentation why there is this weird red and blue robot and why there's an IKEA Kallax shelf in this picture. So I hope this is at least some kind of teaser to to be interested to listen. Before we dive into what I want to actually talk about, I will just very briefly talk about my research group because I think we are not that known yet because we are also very new. So we are called Robot Assisted Inspection and Repair, and we are part of the DLR, so the German Aerospace Center Institute for Maintenance, Repair and Overhaul. We're located in Hamburg, so in northern Germany, just next to Airbus. And here basically we have basically a whole area of the city which is just focusing on airplanes and all the stuff around it. And you can see also in my background that of course airplanes are a big thing for us. But while this is one of our most important use cases, we are also interested in other inspection and repair tasks. And we focus in this already kind of smaller topic of inspection and repair tasks. We even focus more on those tasks that are done in confined spaces. So everywhere where human, it's hard for them to go there and to see there, or maybe it's very unergonomic to go there. So for example, here you see one of our robots. It's a very simple one. Basically just a few interreal sensors on a stick, which is then on a UR10 arm. And this is like an airplane wing section with a fuel tank. And the robot basically goes in there and inspects this fuel tank. But we're also working on having mobile robots that go, for example, to the landing gear of an airplane in the future. And basically while working on this, we had this goal that we want to inspect a complete area or a complete object, because of course in inspection, it is very important that you get the whole area. Otherwise, you're not sure if you saw a defect or not. However, especially in such confined spaces, it is of course not trivial to have a robot kinematics, which is, or a kinematic structure, which is able to reach all parts of this area of this object. And I guess you will have also similar problems in other tasks for painting or such things where you really want to cover somehow a whole object or area. And of course, we can now try to optimize this kinematic structure. And I already said it, it's kind of an optimization problem. And we tackled this basically by using Reach, because Reach is it's a very nice tool. I like it a lot. Most of you know it probably, so you can use it to see which area a robot kind of can reach. And of course, we could now use this and manually try out different robot kinematics and different styles or whatever. But of course, why should we do something ourselves when a computer can do it for us? To have a nice abbreviation. And this kind of software basically does a more or less simple optimization loop of sampling some parameters, and those parameters are some parameters of the kinematics, and then creating a corresponding or did you lose me for a second there? Sorry. Then creating some corresponding URDF putting this into reach to evaluate how well it works, so to say, and then incorporate those results basically in this kind of small database. And then again, based on this data that we gathered, sample new parameters which are hopefully better than the ones we already had. And yes, and to, of course, as we love open source software, we also used an open source library for optimization algorithms, which is called Optuna. And I personally had already some experience from it from my PhD, where I used it for optimizing skills for humanoid robots. So it's a totally different application here, but still it's a very nice library. And if you ever want to do some optimization for whatever you want, I can really recommend it. It implements multiple kind of well-known optimization algorithms, so TPE, tree-structured Parson estimator, and its GA3, non-dominated sorting genetic algorithm, CMAES, covariance matrix adaptation evolution strategy, and also like stuff like random and so on. We, for now, kind of focus on using TPE because in the past I made a lot of good experiences with it. And basically this whole COI is just a bit of Python code, which kind of, basically glues Reach and Optuna together and does all those a bit things that need to be done but are not so interesting, like creating the corresponding URDF and so on. While I will focus here on just optimizing the area that is reached on the object, it is also possible to do multi-optimization, multi-objective optimization, where you take some secondary objectives into it. So for example, if you want to create a robot, you maybe want to reach the whole area, but you want to keep the number of joints as low as possible, for example. So this would be a second objective in this case. And we can have a look at some examples. So here on the left side, you can see an example of the standard Reach demo. However, we kind of optimize the position where the robot is located. We do this here for 100 trials. That took like 5 minutes on my computer. And in the end, we get the optimal position where we reach the largest area. And we can see that actually the standard position of the robot from the demo is already quite well. So we are just almost at the normal zero position here. I also did a second run where I also basically gave the option to rotate the robot base however the algorithm wanted, and then it is even able to reach a larger area and does not have this kind of black spot here in the center, which is not reachable. And I think this kind of optimizing the position is quite interesting for building also like robot work cells or whatever. But what we were actually more interested in was really not just changing the position, but changing the kinematics of the robot itself. And this is another small demo here where basically a URDF is created for a very simple 5 or 6 DOF robot with just cylindrical joints. And of course, there are some kind of limits for each joint, and there are some kind of limits for how long each link can be. And again, the algorithm tries here 100 different configurations of this robot and then comes up with this one as the most optimal that it can find, which reaches the largest area. And because Optuna is a very nice library, it also directly gives you some additional features like getting insights on this optimization process. For example, here you can see those 100 trials from the example with the serial robot that we just saw. And we can see how kind of the best solution improves over time. We can also see which kind of parameters have the highest importance. So for example, the length of the first link seems to be very crucial in this scenario. And we can also see here that the final result, it kind of minimized this link length here because, it seems to be the best option. yeah, and this was kind of basically the first kind of software that I wanted to show. And then after we did this, we kind of had another problem because we now had a kind of nice kinematics that we could create. However, we had problems that the inverse kinematics did not find, or the inverse kinematic solver did not find solutions very often because we were acting in very collision-rich environments. And yeah, so many solvers had problems with this. And for us, it was not clear which solver is the best one to choose in such a scenario. And also some of the solvers like PIC-IK, their quality kind of depends on some hyperparameters that they have. So again, we basically had the same idea as before. We said like, okay, this sounds like an optimization problem. So why not basically do the same thing again that we did with Koi, but not change the robot around, but change the IK parameters around. So we came up with a second kind of small piece of software that we called e-bike for enhancement and benchmarking of inverse kinematics in environments. And you can see we really like abbreviations. And the idea is here that it helps you to compare, evaluate, and optimize IK solvers in different environments. So we have some kind of standard scenarios here. There's just a normal, like a small table, like a more normal size table, like an IKEA Kallax shelf, and some kind of barrels. But those are just some standard scenarios we ship basically with the software, but it's very easy to add another scenario yourself. And then you can run different IK solvers for this scenario and also optimize their parameters. For the moment, we only optimize the parameters for the PIC-IK solver, but there are more to come. And yeah, the great advantage that we also see here of e-bike, most previous benchmarking, or basically all that I have seen of IK solvers, didn't take really into account any environment. And therefore, they didn't really take into account the ability of those solvers to handle possible collisions. So I think our software is quite interesting to benchmark IK solvers. And if you have more or less special requirements, you can come up with your own scenario. You can put in your own robot, of course, and then see which solver is kind of the best for your case. Yeah, and besides this, I just want to quickly mention some other things that we are working on in case any one of you is interested in this. We are also working on extending reach for inspections. So normally reach kind of tries to solve each of those goals so that the robot kind of reaches this pose. But for inspections, we of course are just interested in looking at this point, which gives you a bit of flexibility for the distance. And you can also look at it with a small angle without really having a problem. So we already have kind of programmed a prototype of this, but it's not merged yet, but we will work on this further in the future. Another software that we did is called BinSpect, which is for visual and inspections and also other inspections. You can see some pictures here. It's a bit inspired from the industrial reconstruction kit, is it called, I think, where we can kind of get a 3D model based on the depth camera information that we have. And we can then actually also get back the original images from certain points, which is very crucial for if you want to do inspections in an aircraft, you cannot kind of rely on some 3D model that you created, but you need to look at the original photos or images. And you can also incorporate other data. So this is, for example, ultrasonic data, where a part is kind of scanned for the thickness and some defects are found here. We're also working on detecting reflections and repositioning of cameras, because in inspection, of course, if you have a large reflection on your image, then you cannot really see if there's a defect or not. And we are also working on some new IK solvers for collision-rich environments, because this seems still to be quite challenging for most standard IK solvers that are out there. Yeah, and that's basically already it. I will gladly take any questions. I also put there some links on the slide and my contact email address if you happen to have some questions tomorrow or whatever. And yeah, I would just say thank you for listening and go ahead with any questions.
I had a question.
Tyler Marr, Southwest Research.
Whenever you're doing the reach optimization, how did you kind of evaluate the quality of the pose? I know you could like see a lot of poses were really good to reach. Some of them were terrible to reach. What was kind of like the benchmark to say, this is the number I'm assigning this pose?
Yeah, so for the moment, we mostly focused on reaching it somehow, not on the quality, so to say. So basically reach gives you kind of this, just how many of those points have you reached somehow, and then this kind of score. We just took this, how many have you reached somehow, for the moment. You can already in Koi also change to the score, and then it also kind of tries to optimize, the score. So basically the manipulability, and because for us, since we are more caring about inspections, it doesn't matter so much from kind of which angle we see it, and therefore we were not focusing so much, I think, on this topic.
That makes sense. And then do you think this could easily be extended to something of like, say you have an oversized workpiece that you want to work on, and you have some n number of robots, and optimize the n number, minimize the number of robots to see everything?
That's actually something I already wrote, like in the README of the repo, that currently it's just for like a single robot, but that would definitely be an interesting addition for the software, in my opinion, because also like when we talk about this positioning thing here, we could also say like, okay, maybe I can get the left side from this position, and then if I position the robot on another point, then I get the right side, and then I have everything. And if I have kind of a mobile robot, then I could kind of use this to kind of solve where I need to drive, basically, and then the mobile robot drives there, the robotic arm on the mobile robot does some work, and it moves to a second place. I think this could be a basis to develop something like this. So we are not so interested in it to do this ourselves currently, but we really welcome any addition or collaboration or whatever.
This is really cool. It's a great idea. I like it a lot.
Yeah,
Thank you.
It's like